50 degrees Celsius, solid granite mountain. Explosives detonating deep inside the earth, one controlled blast at a time. And the city this tunnel is meant to serve, it doesn't exist yet. Welcome back to the channel. What you are about to see is one of the most audacious feats of underground engineering ever attempted anywhere on Earth. This is the story of the spine, the buried nervous system of NEOM's The Line, and the extraordinary human effort to blast, drill, and dig it into existence beneath the Saudi desert before a single resident has arrived above it. This is not just a tunnel. It is not just a railway. It is the backbone of an entirely new kind of city. A city designed from the ground up with no roads, no cars, no exhaust, and no traditional street grid. A city where every resident lives within 5 minutes walk of everything they need. A city that stretches in a single straight line for 170 kilometers, from the shores of the Red Sea deep into the Hejaz mountain range of northwest Saudi Arabia. And the only way such a city can function, the only way 9 million people could theoretically move through it, is if the transportation system running beneath it is flawless. That system is the spine. And drilling it into existence is unlike anything construction engineers have attempted before. Imagine it. You are standing inside a mountain in the Tabuk province. The air smells of cut granite and diesel. The walls around you are raw rock, blasted and chipped back meter by meter. The heat outside has been touching 50 degrees Celsius. The ground beneath this mountain is arid, fractured, ancient. Above you, eventually, if the plans hold, will rise a mirrored wall 500 meters tall and 200 meters wide, stretching to the horizon in both directions. But right now there is only darkness, dust, and the sound of drilling rigs pushing into stone. This was not a small decision. This was not a simple dig. Before we continue, if you are watching this for the first time, make sure you subscribe to the channel. We cover the engineering stories behind the world's most ambitious construction projects, and we go deeper than the headlines. Stay with us until the end of this video, because what they discovered about drilling through Hejaz rock and what they decided to do with every fragment they excavated is one of the most quietly ingenious decisions in this entire project. At first there was only desert and mountain, no road to speak of, no infrastructure, no workers' camp, no concrete plant, no supply chain. Just the Tabuk province's ancient heat-scorched terrain, sun-cracked granite ridgelines, sweeping valleys of sand and gravel. The silence of a landscape that had never been asked to do anything like this before. No power lines running to a construction zone of this scale. No water infrastructure for tens of thousands of workers. No foundation for even the first pile. This is where it started. The engineering problem is deceptively simple to state and staggeringly difficult to solve. The line has no cars, no roads, no surface transport of any kind. Not buses, not trams, not bicycle lanes. It is designed as a vertical city, a 170-kilometer corridor that houses people on multiple levels, with everything from parks to schools to workplaces stacked on top of each other rather than spread out horizontally. If you want to move from one end of that corridor to the other, there is only one way to do it: underground, at speed. If you put the transportation on the surface, you break the fundamental promise of the city: no cars, no roads, no noise, no pollution. If you put it on top of the structure, you lose the sky. If you do nothing, you have 9 million people trapped in a 200-meter-wide corridor with no way to move between districts. So the solution was not a metro line, it was not a conventional subway, it was a dedicated high-speed rail spine buried deep beneath the city, running the full length of the line, designed to carry passengers from one end to the other in approximately 20 minutes, at speeds in the original design projected to exceed 510 kilometers per hour. The engineers called this infrastructure the spine, and it required tunnels, enormous tunnels, long tunnels. Tunnels bored not through soft city soil, but through the hard granite and basalt of the Hejaz range. The decision of how to dig those tunnels was itself a critical engineering choice, one that had major consequences for cost, speed, safety, and environmental impact. The first option on the table was tunnel boring machines. The enormous mechanized worms that have dug the Channel Tunnel, London's Crossrail, and dozens of other great underground projects of the modern era. TBMs are precise. They produce a clean, consistent tunnel diameter. They are safer for workers because much of the excavation happens within the machine's protected shield. They create less vibration and disruption at the surface above. But TBMs have a critical weakness in the Hejaz mountain geology. They are expensive, prohibitively so on hard, dry rock where their cutting heads wear fast. They are slow to mobilize. Each machine must be custom-built, transported in pieces, and assembled underground. and they work best in continuous, consistent ground conditions. The fractured, variable granite of northwest Saudi Arabia, alternating between solid bedrock and loose, broken rock zones, is not where a TBM performs at its best. So the solution was not a TBM. It was not a simple conventional excavation either. It was the drill and blast method, a technique as old as modern tunneling itself, but deployed here at a scale, in a temperature, and under a schedule pressure that pushed it to its absolute limits. In June 2022, NEOM awarded 2 major drill and blast tunneling contracts. Both contracts together covered more than 28 kilometers of underground tunnel work, 2 parallel tunnels designed to run the length of the initial spine section, one dedicated to high-speed passenger rail, the other to freight. The total tunnel infrastructure required was not a single dig. It was a coordinated, multi-front assault on the rock of northwest Saudi Arabia, divided by geography, lower and upper sections of the route, and executed simultaneously by different contractor consortiums, working toward each other through the mountain. The first contract went to a joint venture of 3 construction giants: FCC Construction of Spain, China State Construction Engineering Corporation, and Shib Al Jazeera Contracting Company of Saudi Arabia, a consortium bringing together European tunneling expertise, Chinese construction scale, and local knowledge of the Saudi operating environment. The second contract went to another consortium, Samsung C&T of South Korea, Hyundai Engineering and Construction, and Saudi Ark-Rodan Company. Korean engineering precision combined with proven experience in large-scale infrastructure. Then came the actual work of drilling into a mountain. The drill and blast cycle is methodical, dangerous, and relentless. Every single meter of tunnel progress involves the same sequence of steps, repeated over and over and over again, month after month, in darkness and heat and rock dust. First, a team of drillers advances to the tunnel face, the raw rock wall at the forward edge of the excavation. They position their equipment with precision and begin drilling a pattern of holes into the face. Dozens of individual boreholes arranged in a carefully calculated geometry at specific angles and depths. The pattern is not random. Every hole is positioned by an engineer who has studied the rock's fracture lines, its grain, its weaknesses. The goal is not to shatter the rock unpredictably, it is to break it in a specific shape, advancing the tunnel by a controlled distance with each blast, producing fragments of a manageable size and, critically, not destabilizing the rock surrounding the tunnel. Then came the charging. Workers thread explosive charges into each borehole, connected by detonation cord in a precisely timed sequence. The sequence matters enormously. The inner holes fire first, creating a void into which the surrounding rock can collapse. The outer holes fire next, breaking the perimeter. The timing is measured in milliseconds, a choreography of controlled destruction, fine-tuned for this specific rock, at this specific depth, in this specific section of the tunnel. Then came the blast. The crews withdraw, the detonator fires, the mountain groans, dust fills the tunnel in a wall of gray, and when it clears, if everything has gone correctly, the rock face has moved forward by another 2, 3, 4 meters. The tunnel is that much longer. But blasting is only the beginning. Then comes mucking out. Excavators and loaders move into the smoke and dust to break the blasted rock pile into manageable pieces. Trucks, fleets of them, operating in the confined space of the tunnel on ventilation schedules that keep the air breathable, haul the shattered stone back out to the surface. Hundreds of thousands of tons of rock, trip by trip, load by load. Then came something that speaks to the ambition of this entire project. NEOM's engineers made a decision that is rare in large-scale tunnel construction. Almost none of that excavated rock would be wasted. The fractured granite and basalt being blasted out of the spine would be crushed, processed, and fed back into the project itself, incorporated into the permanent concrete lining of the very tunnels it came from, and used in other construction works across NEOM. The mountain would help build its own tunnel. In a project where environmental claims are central to the entire vision, this closed-loop approach to excavation waste was not a small detail. It was an engineering philosophy made literal. Then came the shotcrete. Immediately after each blast, once the rock face has been cleared and assessed for stability, a team of workers advances to spray the newly exposed tunnel walls with a layer of shotcrete, a fast-setting concrete mixture projected at high velocity from a nozzle, coating the raw rock surface and binding loose fragments in place before they can fall. Rock bolts are drilled into the tunnel crown and walls, anchoring the rock mass above into a stable arch. Steel mesh is pinned to the surface. In the most difficult zones, fractured rock, water seepage, fault lines crossing the tunnel alignment, steel ribs are erected and packed tight against the walls, forming a skeleton of structural steel inside the mountain. Every bolt mattered, every spray of shotcrete mattered, every measurement of the tunnel's deformation, engineers monitoring instruments embedded in the rock, watching for millimeters of movement that would signal a zone of instability ahead. Every reading mattered. The tunnel was not uniform. The geology changed constantly. There were sections of clean, hard granite that drilled beautifully and held their shape with minimal support. There were sections of fractured, water-bearing rock where the tunnel walls wanted to squeeze, where the ground above the crown shifted, where water seeped through cracks and had to be channeled and pumped out in continuous streams. There were fault zones, ancient fractures in the Earth's crust, where the rock on either side had moved at different rates over millions of years, leaving bands of crushed, unstable material that required extraordinary care to pass through safely. Meanwhile, at the surface above the mountain section, a separate and equally complex challenge was underway. The spine was not just a rock tunnel in the mountain. For sections where the line runs through lower-lying ground, across sandy desert flats, through the wadis and alluvial plains between the mountain ridges, tunneling required a different approach entirely. Here, where the desert floor is made not of granite but of loose sand and gravel, the drill and blast method is useless. You cannot blast sand, you cannot drill it the same way. The solution in these zones was cut and cover construction. The ground is excavated from above, the tunnel structure built inside the pit, and the surface restored over the top. This demanded its own infrastructure miracle. NEOM deployed a fleet of 10 high-capacity rotary drilling rigs, machines capable of sinking foundation piles into the sandy ground to depths of 60 to 90 meters, with diameters of 2 to 2.5 meters in one of the most difficult geological environments imaginable. Fine desert sand that wants to collapse into every hole before the concrete can be poured. In this zone alone, those rigs collectively drove more than 4,500 piles just in a single module area at a peak rate of 60 piles per day. Then came the dewatering. Beneath the desert floor, this close to the coast and the ancient water table of the Hejaz, groundwater is everywhere. Before any deep excavation can happen, the water must be removed. NEOM implemented what has been described as one of the largest dewatering operations in construction history. Thousands of wells, pump stations, and drainage systems running continuously to lower the water table along the entire construction corridor, meter by meter, allowing excavators to dig down to the depths required for the spine's underground levels without flooding the works. By February 2024, the scale of what had been moved was staggering. Over 90 million cubic meters of earth and rock had been excavated and relocated across the line construction zone. To put that in context, that is enough material to fill roughly 36,000 Olympic swimming pools. That is more than the total excavation volume of the Panama Canal. Then came the Adit tunnels, a detail of the construction that most people never think about, but which is essential to the entire operation. An Adit is a horizontal access tunnel driven from the side of a mountain into the interior, intersecting the main tunnel alignment. It serves one critical purpose. It creates additional working faces. Instead of digging a 28-kilometer tunnel from just two ends, which would take decades, the engineers drive access adits at intervals along the route, reaching the main tunnel alignment from the side, and then dig in both directions from each junction simultaneously. China Railway Construction Corporation alone completed one of 6 Adit tunnels covering a combined length of approximately 9.48 kilometers in the mountain section. Tunnels within tunnels, a labyrinth of access corridors feeding the main excavation from multiple points at once. With 6 access adits, the construction team multiplied its working faces. Instead of 2 faces, they had 12 or more. Instead of advancing at one rate, they were advancing simultaneously from many points. The rate of progress, measured against the sheer volume of rock being removed, climbed accordingly. Then came the fit-out. An empty tunnel is only the beginning. Inside the spine, once the rock has been cleared and the permanent concrete lining installed, the work of turning raw space into functional infrastructure begins. The systems required inside a high-speed rail tunnel of this complexity include not just the track itself, but an entire parallel universe of infrastructure. High-voltage power cables running the full-length emergency lighting systems, fire suppression and detection equipment, ventilation shafts and fans sized to clear smoke from the tunnel in an emergency, drainage channels to manage any water intrusion, cable trays carrying communications and signaling systems, emergency egress walkways, maintenance access doors at regular intervals, catenary systems to carry electrical power to the trains above. All of this built, integrated, and tested inside a tunnel in the desert, at depth, in heat that does not forgive mistakes. Every cable run mattered. Every ventilation calculation mattered. Every egress door mattered. Then came the concrete plant. This is the detail that reveals the true industrial ambition behind what NEOM is attempting. Concrete, ordinary concrete, is the material that everything depends on. The tunnel linings are concrete. The pile foundations are concrete. The structures above ground will be concrete. In a project this size, you cannot rely on ready-mix trucks driving from a city. There is no city. So NEOM commissioned its own dedicated concrete manufacturing facility at a cost of approximately 700 million Saudi riyals, close to $190 million. This plant, built specifically for the NEOM construction zone, is capable of producing up to 20,000 cubic meters of concrete every single day. And critically, some of the aggregate fed into that plant comes from the crushed rock excavated from the tunnels themselves. The mountain, broken open to build the spine, helps manufacture the material that lines it. Then came the revision. This is the part of the story that no promotional video shows. In 2023, NEOM announced a reduction in the scope of the initial spine contracts. The number of planned stations along the spine was cut from 48 to 9. The freight rail, originally intended to have its own dedicated tunnel, would now share infrastructure with the high-speed passenger system. The commuter line connecting local communities would be built in a later phase. The tunnel length contracted to cover a reduced initial scope, and by early 2026, the tunneling contract held by the Samsung Hyundai Archiroden Consortium, a contract worth approximately $1 billion, was terminated, with settlement for completed work finalized. These are not secrets. They are the reality of building something no one has ever built before, in a part of the world where the heat alone is a daily engineering problem, against a timeline that the finances of the global oil market do not always support. Most people who will one day ride the spine will only feel its absence. They will not see the tunnels. They will board a capsule in a station, feel the acceleration, and arrive somewhere else 20 minutes later. They will not see the 6 Adit tunnels driven through the mountain to create working faces. They will not see the 10 drilling rigs sinking 90-meter piles through desert sand in the dark. They will not see the 90 million cubic meters of excavated material moved by trucks and machines over years of work. They will not see the concrete lining, meters of it, installed panel by panel around the tunnel walls after every blast. They will not see the ventilation systems designed to sustain human life at speed underground in a desert where the air outside is the temperature of a sauna. They will not see the dewatering wells running night and day to hold back the ancient water table. They will not see the workers from dozens of nations, Spanish, Chinese, Korean, Saudi, Indian, Bangladeshi, working in shifts, underground, in heat, drilling the same cycle over and over until the mountain gave way. They will not see any of that. They will only see the destination. Without the spine, the line is a wall. With it, it becomes a city. Without the tunnels, the entire premise of a car-free, zero-carbon urban corridor 170 kilometers long is mathematically impossible. Every decision, to use drill and blast over TBM, to reuse excavated rock as concrete aggregate, to drive 6-axis adits through the mountain, to build a dedicated concrete plant from scratch, to sink pile foundations 90 meters into the desert sand, every single decision connects to every other. The spine needs the piles need the concrete needs the crushed rock. The crushed rock came from the tunnel itself. This is not just engineering. This is an argument made in steel and stone and concrete, that the way human beings live in cities can be changed, fundamentally, permanently, and at scale. Whether the line becomes everything it promises or evolves into something different, the tunnels being drilled beneath the Saudi desert represent something real and verifiable. Thousands of meters of rock have already been cleared. Hundreds of foundation piles have been driven. Concrete is being poured. The mountain has already given way, section by section, blast by blast. Someone decided that this was possible, and they are doing it in one of the hottest, most remote, most geologically challenging places on the planet. Not for a city that exists, but for a city they believe will exist. That is the engineering miracle hidden beneath the sand. If you found this story as extraordinary as we did, make sure to subscribe to the channel. Leave a comment below. Do you think the spine will ever carry its first passenger? Or is this the world's most ambitious engineering exercise? Next time, we are looking at another mega project where the geology nearly ended the dream before the first wall went up. Thank you for watching.